Okay, so today we're going to go over the equivalence principle. Now, the equivalence principle is something that Einstein discovered when he was in his young teens or 20s or somewhere around there, where he found out that if he was in an elevator, and before I actually get into this thought experiment, this is called the equivalence principle. The equivalence principle. And so Einstein's thought experiment was, okay, I'm in an elevator, and so I'm in an elevator, and I theoretically shouldn't be able to tell whether or not I'm accelerating upwards if I'm in this elevator or I'm in free fall. Right, so here's two instances of the elevator, and here I am in the elevator, and basically creating a copy here. Now I shouldn't, if the elevator is being pulled this way, then I should theoretically feel no difference at 9.8 meters per second squared. I theoretically should feel no difference, or there should be no noticeable difference if I was in free fall on the Earth, if this elevator was falling down, right? So there should be, this is the equivalence principle, right? And a lot of people in general relativity, a lot of students in general relativity will think, okay, that makes sense. Who cares though? Well, so here's why this matters. We're going to beat up this idea of the Christoffel symbol again. There's going to be multiple videos probably on this Christoffel symbol because, again, this object here, this mathematical object, is essential to help us understand general relativity so that we can get a really good foundation before we move into some really advanced stuff. And so the equivalence principle basically says this. It basically says, give me a vector, big X mu, right, and take its double derivative with respect to time. Okay. This is the equivalence principle, that if I have some vector in some frame of reference, if I have some vector and I want, or some function, and I take its time derivative, I want to get a value of 0. Okay. You could think of this as, okay, I'm in some Cartesian coordinate system, and here's my vector. Here's my vector. Right, I can perhaps find the slope of that. So the slope is not 0 of this vector. But then the slope of the slope is going to be 0, right? Because it's just a straight line. So this is the most literal interpretation of the equivalence principle. And the reason this stems from the equivalence principle is, again, is because there is no difference between this form of acceleration and this form of acceleration. So therefore, these vectors, if you will, sort of cancel out, and we get this. So this here is the equivalence principle, Einstein's equivalence principle. So, and some people might call it the EEP, Einstein's equivalence principle, EEP, like this. And so so if there's no difference between these two situations, and therefore no net acceleration, in other words, the acceleration is 0, what are the inevitable consequences of this equation? Well, we can start off by saying, well, okay, the derivative of x mu dx with respect to t is equal to, sorry about my dog in the background there, she yawns really weirdly, is equal to dx nu d, I'll call this, actually no, I want to call that t, dt, and dx mu, I want to call this big X. This is sort of a big X here, like that. Big X, d little x mu. So this is the derivative of our vector with respect to its coordinates, its spatial coordinates, and then the spatial coordinates with respect to time. Okay? We can therefore expand this out a little bit more if we were to take the double derivative. Dx mu, this is a big X again, with respect to dt squared. Well, it's equal to the time derivative of this. Right, so, well, the time derivative of this is with the chain rule. It's going to be dx nu squared with respect to time times this guy, so which is d big X mu dx nu, plus this guy here, dx nu, times dt, times the time derivative, or times the second derivative of this guy right here. Right, so the second derivative is going to be, well, I have to do a dx alpha dt, and then I put my dx alpha down here, and then my dx nu, that was there, and then my dx mu. And again, this thing we said was equal to 0, so this whole thing is equal to 0. This is Einstein's equivalence principle, that this is equal to this. Therefore, all of this has to equal 0. Okay. So where do we go from there? Well, again, this video is actually going to be kind of short, I think, because I just want to look at the equivalence principle. So where do we go from there? Well, we could say that this, we move some things to the other side of the equation. Dx squared dt squared times dx mu, this is a big X again, times dx nu. Remember, again, nothing is really stopping us from saying, well, this is kind of the same thing as dr mu. This is just the name of a vector, right? I think in the last video I used an r. In this video I'm using an x mu. Because again, we're going to see different notations, so it might be useful for us to understand different notations here. All right, well, this is equal to the negative of this because we're just moving it to this side of the equation. So this is going to be, again, I apologize in advance for my dog's noise. Dt times all of this sits in the parentheses. Dt, and then d, this should actually be a squared right here, d squared x mu with respect to two summed over coordinates, like this. And then we get this expression. Okay, well, we can multiply. Let's say we want to get rid of this numerator here. Well, we could say that this guy right here, if we could just multiply both sides of the equation. Sorry about that. Dt squared dx mu dx nu. And I want to just multiply this by dx lambda. This is just sort of another dummy variable. Dx mu. Right. Again, these are all summed over. A lot of these are going to be summed over. So like nus are going to be summed over, mus are going to be summed over, and we get this over this. Well, the purpose in doing this is just to see a realization here, where we see that dx nu dt, right? And then we put everything else in the parentheses. Actually, I will take the parentheses out because this is just straight up multiplication now. This is dx alpha dt d squared x mu, oops, let's see here, this is a mu dx nu dx mu, and then we're multiplying this by this guy over here. We're just doing the same thing to both sides of the equation. Dx mu. Right, well, we realized this guy, well, what is this guy? We established earlier on from the extrinsic formula for the Christoffel symbol that this was the Christoffel symbol. And so we end up getting that dx lambda with respect to time, so we have this extra d out here, so dx lambda with respect to time squared, so the double derivative is equal to these guys, so the negative, wait, we can actually absolve the negative into our Christoffel symbols. I won't though. We have dx nu dx, or dt, and then dx alpha dt times our Christoffel symbol, gamma nu alpha. This is the equivalence principle. This is a direct consequence of the Einstein equivalence principle, where this guy, if I were to just sort of explain really quickly here, this guy shows up. This guy is an inevitable consequence. And it tells us that when we take the derivative of a vector, or the second derivative of a vector, and we invoke the Einstein equivalence principle, the result can only be another double derivative of a vector if we invoke these Christoffel symbols. Right? So again, sort of the double derivative here with respect to time plus our invocation of the Einstein equivalence principle leads us inevitably to our Christoffel symbols. Right, I have those mixed up, but this is a derivation of the Einstein equivalence principle, showing that if we were to invoke this, we get these guys, right? And then again, these guys are linked to our metric tensors, d mu nu, right? Through our extrinsic and our intrinsic formulas, right? So this guy right here, there's an extrinsic formula for this guy, then there's an intrinsic formula, and then there is the derivation by means of the Einstein equivalence principle formula. So this guy is very important. And then he's linked to these guys through those guys. So I don't want to be a little bit more precise here. This shows us that this guy is linked to this guy right here. And so with that being said, our picture now is we have some space-time We have some space-time, and at each point, not only do we have our metric tensors, but we have our Christoffel symbols as well. And with that being said, this is a pretty short video, but with that being said, I will move on to the next topic, and I will see you in the next video.